Students, welcome to the lecture number 6, and this is the course on AI/ML in materials engineering. Hope you are enjoying the lectures, and in this portion of the lectures I have been discussing about the basics of material science. So, let us continue on that, because these aspects you must have clear idea in your mind if you want to design materials using machine learning or deep learning approaches. So, first obviously we are going to do some recap as usual, and I have been telling this again and again to you that basics of material science engineering is basically the connection between processing, structure and properties. Almost all materials are processed to give different kinds of components, right. So, hence you want to make something out of a material, you need to use some processing route, and depending on the type of routes you are going to use, the material structure will change, and that is why you can create different kinds of structures, and which in turn will have a direct correlation with the property. So, that is why it is important to understand these certain aspects, so that you can actually design materials with target properties and hence use structure as a playing ground to achieve those properties. So, with this let us begin, and structure means different kind of structures. This I have been telling you again and again, please keep in mind, that is why we have been telling. First one is obviously atomic structure, because every material in this world is made of a basic element or basic unit called atom, and when atoms actually assemble, it can form crystal or amorphous structures. We have not discussed yet amorphous structures so far, we will do it later. So, we have discussed about crystalline materials. So, once at a group of atoms come together and they arrange in a definite way or regular fashion, that form a crystal, and when the crystals actually arrange in the 3-dimensional space, they can form microstructure. And properties means we are talking about mechanical, physical, magnetic, electronics, electrical, all these kinds of properties. You are important for you to understand or rather fully understand this correlation between structure with the properties. And as far as crystal structure is concerned, most of the metals actually crystallizes in 3 different structures. First one is a body center cube, that is called BCC structure, and it has a very simple unit cell. I can draw it here and show you that. Okay. So, this is the unit cell, you can draw your cell, that is why I am drawing, and in this unit cell each corner will be occupied by one atom. Along with that, you will have a atom in the center. Now, center atom can be different type or same type. If it is different type, then it is a order BCC structure. Forget about that, simply consider the central atom is all same type, then it is basically called a simple or BCC structure. Okay. So, that is what it is, because this atom is at the center of the unit cell, that is why it is called a body center cubic structure. Very important materials like iron, molybdenum, tungsten, chromium, these are widely used, they crystallize in this structure, and that is why it is important. In fact, there are other materials also have shown this kind of crystal structure, many ceramics also. Well, second important structure which we discussed, which is prevalently present in material system, is face center cubic structure. So, therefore, let us say I draw the unit cell. So, you should follow me, because this is something you should know very well how to draw it, otherwise if you want to teach like me, you may not be able to do it yourself. This is a cubic unit cell. So, now place the atoms. So, you have atoms at each corner of the unit cell, right, you can see that, and you also atom in the face centers. So, there are 6 face centers, that is why there are 6 atom in the face centers, and there are 8 corners. That is why the face center cubic unit cell. And in this case effective number of atom is 4. Why it is 4? Because each corner atom is giving 1/8 because each unit cell can be shared with 8 other unit cells, which you can do yourself very easily. That is so 1 by 8 into 8 is 1, and each phase is shared with another unit cell. That is why each phase center atom gives half. So, 6 into half is 3. So, 1 plus 3 is 6. For body center cubic unit cell, the effective atom is 2. You have 8 atoms in the corners, that gives 1 atom, 1 by 8 into 8, basically 1 by 8 into 8, plus the central atom is inside the unit cell. So, it belongs to the unit cell, that is why it is 1, that gives you 2. So, I can write down 1 by 8 here into 8 plus half into 6, that gives you 4. So, this is the effective number of atoms in the FCC unit cell. That is why you see FCC is more dense packed structure. The body center cubic structure has about 68% space is filled, and phase center cubic has about 74% space is filled. So, body center cubic structure is more open than the phase center cubic structure. Phase center cubic structure is called a close packed structure because atoms are basically touching each other in this kind of structure. Body center cubic structure is not a close packed structure. So, many important metals like copper, which is used in electrical applications, silver, gold, nickel, lead, aluminum actually form phase center cubic structure. If you know ceramics like carbides, many of the carbides actually form phase center cubic structures. Tungsten carbide is one such, niobium carbide, many carbides actually form phase center cubic structure. And the last important structure is hexagonal close packed structure, and this structure is also widely seen in material system, okay, both in metals and ceramics. So, let me draw an hexagonal cubic unit cell. So, first I draw an hexagon, and I will draw a little bit perspective way, so that you can see the whole unit cell very nicely. This is an hexagon, then I take these things up, connect it, I also take this up, connect it, then I also take this up, connect it, okay. Then this one, connect it, okay. This is a hexagon. Yes. Now, you can see here hexagon has a, each face of the hexagon has a center. Center is occupied by one atom, corners of the hexagon is occupied by, each corner is occupied by one atom. So, and in addition to, there are 3 atoms inside. Okay. So, actually speaking, if I draw this one, let us do that, yeah. I can take out this unit cell, which you can clearly see. I am marking it with this red color thing. I will draw it here also. I draw it here for your purpose, so that you can understand. This is a rhombohedron, okay, not a cube, rhombohedron, basically rhombus in 3 dimensional. So, each corner of the rhombus has one atom, and here at the center you have one atom. So, therefore, how many effective number of atoms hexagonal cubic crystal has? Let us do it from the hexagon. 6 will be 1 by 6 into 6, and that means 6 plus 6 is 12. So, 12 1 by 6 by 12, and then there are 2 atoms on the face center. So, 1 by 2 by 2, because this is shared, and there are 3 atoms inside. So, 2 plus 1 plus 3 6, right, and here you see there are only 2 atoms, because inside one atom and there are corners as 8 corners as 1 by 8. So, you can consider each of these, any of these as a unit cell, does not matter. That is how it has to be understood. Hexagonal close packed structure is close packed again, it has 74% space occupied by the crystals, only remaining space about 36% space is vacant, just like a face centered cubic structure. And many of the important metals, magnesium, titanium, zinc, as well as many of the ceramics will crystallize in this, like aluminum oxide, okay, is one of the important ceramics which forms hexagonal crystal structures. Many ceramics are there, I can't remember all of them now, but they form this crystal structure. These 3 actually are very important, they are very important crystal structure in materials. They are widely seen in material system. They are widely seen in the material structure. So, therefore, please remember these aspects very well. Now, from the crystal, how do you start form the microstructure? Very easy. You can actually put crystals large numbers and form grains, right. I already talked about it, and then between two grains you will have boundaries where the atoms are not arranged properly, haphazard. That is why they are called grain boundaries. So, by this way you can form the whole microstructure. So, now you can see that there are two aspects here in a normal material in the microstructures. One is the grain, where arrangement of atoms are regular, another one is the boundary. That is why the boundary atoms are haphazardly aligned or placed. So, therefore, grain boundaries are having lot of free space present, where atoms can migrate, lot of things can happen, okay. And this is an important area of subject. And grain boundaries can also be different types, which we are not going to discuss, but there are different types. They can also play a role in determining the mechanical physical properties. This is a picture of the optical micrograph of pure iron. You can see here, this I have been showing you for last 3 lectures. So, after that we talked about something about imperfection. This is very important actually, that is why I am talking to you again and again, because no crystal is perfect, including silicon single crystals which you use for your devices like mobile phones or laptops or any electronic devices, by the way, washing machines. They have chips, and each chip has silicon single crystals. So, they are also not perfect, there are defects inside it. So, imperfection can arise from because of inability of solidifying material to continue replicating the units properly, or it can be also introduced purposely, like alloying can lead to, or deformation can lead to. The 3 types of defects we talked about it: point defects, line defects and polarity defects. Point defects is nothing but a vacancy. So, in a metallic structure, vacancies have no charge. So, it can be simply vanishing of one atom from its location, like here you can clearly see this one atom here is missing. So, this atom here is missing, right. So, this is what is called a vacancy, but for ceramics this is charged compounds or charged materials. So, therefore, you cannot have one atom missing, this will lead to imbalance of charges. That is why either you have both the atoms missing, that is called ionic pair vacancy, or you can have interstitial possible, then there is no loss of any charge, or otherwise you can have Frankel defects, like atom is displaced from its original position to some interstitial position. Okay, this is very unstable situation, you can see here atom cannot remain, but nonetheless it happens. So, you can create all kinds of defects. Then you have a line defect, which is nothing but a connected group of point defects that form a line in lattice structure, and we talked about 2 dislocation, edge and screw. This edge dislocation is nothing but an extra row of atom, you can see here, this is the extra row of atom here, this one which is missing at the bottom below this, and this is your slip plane, correct. That is why this is the symbol it is used. And screw dislocation is basically it is just like a spiral within a lattice structure wrapped around the imperfection line. It is just like a screw. If you take a screw and put inside a wood, so that is what it will look like. It is a screw moving inside a crystal. So, if you look at from this side, it looks like a screw. So, you can also have planar defects, defects which are extend in plane, like boundaries, like twinning is one such, grain boundary is another one. Twinning is basically a large scale deformation. It is such a way that one part of the crystal is a mirror image of the other part of the crystal. That is what a twin is called. You can see there is a twin plane here. This part of the crystal is a mirror image of this part of the crystal. Same thing here, twin plane can be extended area also. This part of the crystal is a mirror image of the other part of the crystal on this right side. So, in the microstructure it will look like this kind of objects. You can see that it is an extra row atom. That means, if I draw a grain, it will look like this. That is what is a twin is. So, this is something which you are understanding slowly, that atoms, the chemistry of or species of the atoms, they are the most important unit of the materials, and it is not only that, it is the way they arrange in a crystal that actually is from the internal structure of the material. So, internal structure we mean arrangement of the atoms basically, and this can dictate microstructure, substructures, or even many other things which we are not talking about it. In addition to that, you have electronic structure. Electrons actually bonds with different atoms, and that also dictates material properties. Yesterday's in the last lecture I talked about it. So, let us talk about little bit more on this. So, this is something I showed you, that atoms are the basic unit, they form crystal form microstructures or structures, okay, here, and then it forms a component. So, this is macro scale and this is micro scale. So, there is a connection between these two, and this connection is basically trying to understand microstructure will consist of phases and the defects, and defects can be vacancy, dislocation, twins, gain boundaries, voids, cracks, everything, and this can be controlled by these processes, the casting, metal forming, powder, metallurgy, welding or machining. Okay, so I will not talk much of these aspects, we will directly go to the engineering materials which we started in the last lecture. Engineering materials can be two types, metal and non-metals. Non-metal means polymer, ceramics, composites, and metals means ferrous and non-ferrous, because ferrous is the largest quantity we use in the world. We produce about 1800 million tons of steels per year in the world. So, that is why it is the largest one of the material used after concrete in this world, and that is why they group together in ferrous, and everything else is non-ferrous. So, ferrous metal means steels. Steels are nothing but iron and carbon alloy with a little bit of carbon, about 0.02 to about 2% carbon, and they can be plain carbon steel. Alloy steel, plain carbon steels will have no alloy elements added. They are basically like having carbon concentration varying from 0.2 to 1 weight%, and some other things like impurities like phosphorus, sulfur or manganese can be present. While the alloy steels have many alloy elements like chromium, nickel, tungsten, moly, they are added intentionally to create alloys. So, this phase diagram I do not want to discuss much, but let me only tell you that this is the basis for the steel and cast iron. So, steel composition is varying from about 0.0 to about 1%, cast iron percent about 3.5 to about 4.5%. This is what it is, carbon concentration. So, this part of the phase diagram is important for steel. So, here you can see this is FCC austenite phase, and then you have ferrite, this is called BCC phase, this is alpha iron, and then you have cementite, which is nothing but a carbide. I already discussed about it, that if you add carbon to iron, it is going to form carbides. So, this is this mixture of iron and carbide which actually gives you the best properties of the steel, and steel is a material which can be modeled actually very interestingly. It has a lot of data to do a machine learning based or deep learning based models. So, in a microstructure there will be two types of things possible, one is a solid solutions, other one is a compound. So, let us talk about a little bit of solid solutions, because solid solutions are more widely seen, like here in case of iron carbon, this austenite which is FCC solid solution of iron with carbon. So, carbon is small quantity, but iron is the largest species, large species means majority species, and carbon is added in a minute quantity. That is why this is a solid solution of carbon in iron. Similarly, alpha also is a solid solution, but it has very less amount of carbon, about 0.02 weight% of carbon. That is what, but cementite is not a solid solution, but it is a compound. Okay. So, in a phase diagram or a phase mixture, you can either have a solid solution or have a compound, and compounds can be fixed stoichiometry or can be variable stoichiometry possible. So, but here Fe3C is a strict stoichiometry, it has a fixed composition of carbon about 6.67 weight% carbon, and so Fe3C if you look at it has carbon about 6.67 weight%, and iron is remaining, that is about 93.33 weight%. So, total will go up to 100%. That is what is the content of carbon, but it has a fixed stoichiometry, that is you cannot change carbon concentration much in the Fe3C or cementite. So, that is what we are discussing a little bit more in detailed manner, so that I understand. So, what are solid solutions? They are less like a liquid solution. If I take sugar and put in water and stir it, sugar will dissolve in water, and that is nothing but a liquid solution of sugar in water. You can add even salt also, that will also dissolve in water, right. Or let us talk about even glucose in water. You add glucose into water, it will form a liquid solution. Whether same thing can be done in solids or not, that is the question actually we are asking. Yes, it is true, same thing can be done in solid also. If I add nickel into copper, it forms solid solution. Difference between solid and liquid is what? Only in state. Liquid means it is liquid state, solid means in solid state. So, here we are showing a phase diagram of copper and nickel. This side is copper and this side is nickel. So, this is copper side, this is nickel side, you can see this is 100% nickel, this is 100% copper, pure nickel and pure copper, and in between you have a length separate region is what is called liquid plus solid region, below which you have a solid solution called alpha. And since nickel and copper both form FCC, right, nickel copper you have seen both of them form FCC crystal structure, they have a similar like lattice parameters and they are both are metals, same almost similar row of periodic tables, no not same row of period, same column, but they are similar properties actually. So, they mix together nicely and form solid solution. That is something which is unique for the nickel and copper, and this is what it is shown. So, in all concentration of nickel and copper you can form solid solutions. So, we will show you in a detailed manner. Solid solutions can be two types. One is where you add substitutional solid solution, that means you are adding an atom which is replacing the other atom, like if I take a nickel and replace nickel atoms by copper, then it is form a substitutional solid solution. You can see here copper and zinc also form a substitutional solid solution. Right hand side you can see here these are zinc atoms, these grey atoms, and the other atoms actually copper. So, you can have mixture of two atoms possible. On the other hand, you can also have interstitial solid solution. What are these? This is actually Rn atom, let us say, and these are carbon atoms. If atoms are the solid solution atom is small, solute atom is small. Okay. By the way, here the majority atom is called solvent and the minority atom is called solute, very clearly, right. Solvent atoms are actually large number, solute atoms are small number. That is why they are solvent atoms called majority and solute atoms are called minority. So, here you can see both of them have same size, almost similar size, right. Copper and zinc has almost similar size, copper and nickel has almost similar size, but iron and carbon has different size. Carbon is very very small compared to iron. So, it cannot replace a carbon iron atom, it can only goes into the voids or the interstitial positions of the iron lattice. So, iron has a FCC or BCC lattice, it can go there, that is what it is. So, you can see in the 3-dimensional picture also the black atoms are carbon atoms. So, we will talk about much how this voids, already we have talked about some about the voids and other things, tetrahedral voids in diamond cubic structure. We will talk more about it, how these atoms can go inside these voids and form a solid solution in the next part of the lecture. Thank you.